Since joining Shell in 1989, John has focused on catalyst development programs, including hydrocracking, olefin oxidation, alkylation, and future growth. Please welcome. Please join me in welcoming him for our keynote speaker, John.
So this is a real pleasure for me because we've seen a lot of talks on oxidation, and there seems to be a resurgence in the interest in this field, which is great to see. What I want to do is tell you a story, take you back to where it all started, walk you through the Shell journey in particular, with a little bit of a sidetrack, and our role in this. So I call it the ethylene oxide journey. I did put catalyst in the title because there is a bit of process in this. Well, we can go through this line by line if you like. The lawyers made me put it in. It's, if you really want to base your purchases and investments in Shell stock on what I have to say, I don't recommend it. You shouldn't do it. So what we'll do is we'll walk through. I'll give you a little overview of what Shell's catalyst business is about, and it's a different portfolio that we have. The original invention, the sidestep to a very important discovery, by the way, and the story behind it. Then I'll walk through some of the more recent inventions within Shell and where we end up. So we're working on nearly 100 years of inventions here. It's really a pretty remarkable story. So.
Use the microphone, John.
Okay, yeah, I'm told I'm soft spoken. Is that right? Yes. Okay. So we've got a global reach, and we sell catalysts to third parties as well as internally, of course. And we have technical support in all of these. We have production facilities in wherever the region needs to be served, and we have three major R&D hubs. I come from the hub in Houston. The mothership is in Amsterdam. And we have one, the most recent one is in Bangalore, India. So that's our reach. We have a large portfolio of catalysts, of course, there's refining catalysts, which is a large portion of our work. But we also have a lot of chemical catalysts we sell in various areas. We also have some environmental catalysts interest as well. Well, the one I want to focus on, of course, is this one, ethylene oxidation. And this is just one format of kind of bellow sheets. We're not actually that big. I think we don't need to belabor this point. Ethylene oxide is a really important molecule. Most all of it is converted into glycols, which is then turned into all kinds of things. I kind of liken EO to its importance to ammonia. I mean, it almost goes back as far in history as well. Ammonia feeds the world. I think EO just clothes the world in some respect. So a lot of it goes clothing. Polyesters, or it goes into coolants, detergents, all kinds of things. It's basically one of those molecules you need for modern lifestyle. So where did it start? It started in 1931. Actually, before that, because there was a patent that was issued by Theodore Ford, who was working at the General Catalyst Society in France, Paris. And he reported that directly epoxidize ethylene. And this is interesting, with air and water, without water being present. And this is the very first report of such a direct oxidation. Before that, it was chlorohydrin based. But the other things that was interesting, this catalyst was just silver metal, different versions of metal. There was colloids, there was wires, there was mirrors, the lowest was there, and powder. But he made some interesting observations that are still present. One of them being that there are promoters that might enhance selectivity. Another one being that CO2 seems to retard reaction. I mean, we still deal with these issues out. But there wasn't any selectivity information given in this, just the fact that he could analyze and detect ethylene oxide in the effluent stream of when he was contacting ethylene with air form. So we all know this reaction scheme. I won't go through it in detail, but the selectivity, of course, is determined by the oxidation rate divided by total rates, and a deceptively simple mechanism. This one's still being debated, believe it or not. And I'm not going to get into that part today. But the isomerization is a key issue with respect to secondary pathway as well. And once you isomerize, you're going to burn the SOI. We don't even see it without liquid reactors. So right after that patent published, our scientists in Amsterdam probably took a train. I don't think they used Google Maps, but took a train down to Paris to visit the fort in these laboratories. And there was a report written by Dr. Lansdowne, who said that it remains to be proven, by careful calculation, because these were pretty low yields and the selectivities were horrible. Whether or not this would compete with chlorohydrin, which is of course the 2-chloroethanol base catalyzed ring closed to form ethylene oxide. And you can see why, perhaps, that it was very optimistic. Pretty forcing conditions over 400 degrees C, and in a mixture that we would never use commercially, by the way, because that's when it was low. And this is atmospheric pressure. But other companies were interested as well. And so carbide chemicals in particular, it's worth pointing out that before and the agency he was with weren't interested in the developments. They were an academic institution. They wanted to sell the patent. So there were a lot of suitors, and carbide chemicals was one of the ones that bought the patent right away. It turns out IG Farben looked at it and eventually purchased it, built a pilot plant, but it was the late 30s, so that never got anywhere before. But we were there with some R&D as soon as those scientists came back from the Paris lab. And they issued this report in 1934. So you can see, and I love this original blueprint from the report. They had to do everything, generate ground ethanol, sulfuric acid. They had to do wet titrations to look at the products out of this. And they made some observations that you could get, and this one's important, you could get a decent catalyst from silver oxalate precursor. This is 1934. If you look at the patent literature today, you see people making these catalysts with silver oxalate precursor. It's still the one to use. It's kind of remarkable. And they also listed a bunch of different metals that might be used as promoters. So selectivity was horrible still, and probably because they were starting to do supported metal conversions and they didn't have a good understanding of the secondary reaction issue and the effect of the supports and how to optimize them. The people persisted. So silver was discovered. So the hunt was on, well, is there some other metal that can do this, right? Because there must be. It can't be the only one. Well, believe me, if you read the patent literature, the academic literature, any literature, people have looked at everything. Probably except for the radioactive ones, all landed back in silver. Silver is unique in this regard. So the research continued with silver, and we're starting to get into conditions now that make more sense. And we started reporting production rates. So this is kilograms of ethylene oxide cubic meter of chemistry hours, STY. And now you see the reporting space velocities, selectivities that are what we're used to seeing for unpromoted systems or slightly promoted systems. Again, they're now using stoichiometric ratio, which is quite hard to do, still a problem. But they still are stuck with no GCs or mass specs to do the analysis. So very tedious, very careful work, and they see now a real reason to pursue this. So now we need to take a side because carbide chemicals commercialize the process. They bought the patent, they commercialized it, and they commercialized what's called the air process. And this air process obviously uses air as an oxygen source. And so you run your air and ethylene through the reactor bed and you feed your EO out. When they built a reactor to do pilot work, they were noticing that the selectivity was supposed to be in the mid-50s or so for air silver. was shooting up, down, oscillating all over the place randomly. No apparent reason. You can find his account in Joseph Birdie's article in The Chapter of Industrial Dust. It's a really interesting read. I encourage you to go for it. But they saw this random selectivity increase well above their expectations, and nobody could correlate it with process conditions. Until one day, a clever engineer correlated the wind direction coming from a vinyl chloride facility that was just started up. This is what you call serendipitous discovery, right? So when the plant for running EO was downwind, that vinyl chloride operation, selectivity would shoot up. When it was upwind, it would go back across what was in between the selectivity. Very so they figured out it was coming in the air, didn't know what it was. They put in fresh carbon beds to scrub the air, and the effect went away. So then the Oxide, Birdie says, what was it in the air? It was oxides or chlorides. And they looked at all kinds of things. But this is seminal serendipitous. This today is still important finding that we still put chlorine, one form or another, into EO reactors. So why is this important? Get back to this scheme. Well, you've seen this already in some of the lectures this morning. Because of the secondary pathway, selectivity is highly dependent on conversion. This becomes an issue because the air process, so once through operation in series flow reactors, and as you get further and further through the series, your conversion levels have to go up and up. And as they do, your selectivity goes down, which is a bit of a problem. So one of the big inventions that came from Shell, this process was that if you substitute air with a pure oxygen source, you could get much higher selectivity, much higher yields. So that became a big deal because now you take that. This quickly replaced the air-based process. You don't build these plants anymore; they've been there for years. There may be one operating in the world still. There's about 150 EO operating. Any new design is basically. This is back in 1950s, 60s. The reason it's so useful is you don't have to run these high conversions like you do in the air process. You can run low conversion, do the recycle, capture the unreacted ethylene, make up the recycle with ethylene and oxygen. There's chloride, organic chlorides coming into the feed as well, and you get your EO much higher selectivities, of course, nowadays. Selectivities are pretty amazing. So this becomes the modern day process starting in late 50s, early 60s. On the tail of that was the discovery that, now remember, with air, you've got an oxygen-nitrogen mixture. Well, they started looking at, because now you can put in pure oxygen, what are you going to do with that stream? So they started looking at other feed gases. Turns out methane is unreactive over sulfur, but it has great thermal properties relative to nitrogen. It also helps with flammability regime with the mixtures that you run in the reactor. So it was determined that you could maximize your yields as well by running methane gas in place of nitrogen. Some plants just start up on nitrogen, switch over to methane, but virtually everybody uses methane where they can. So it's another big invention that's still being utilized. All right, so what I want to do now is walk into more of the modern catalyst development aspects of Shell history. So we're coming up on 100 years. It's kind of remarkable. We'll get sure there'll be more inventions between now and then. But in those 90 years or so, we've got more recently about 30 new catalysts in the past 30 years only. And what we have developed through the years, this is a graphic that's useful to help show the major inventions. It doesn't really do well for all of what the performance is from the catalysts that are developed, because it's really based on initial selectivity. So the very start of the run, first couple of weeks or so, once the catalyst is stabilized. So we'll focus on some of these individually. The first one I want to talk about we call the high activity panel. So this is an invention that occurred in the early 70s, and it was worked by Bob Nielsen in the Houston laboratory. And what he had done was he changed the chemistry, the silver solution that was used to make the catalyst. Originally, the systems just silver nitrate, dissolve it in water, impregnate the area, dry it, put it in a reactor, reduce it with hydrogen. Probably the worst way you would get dispersion, right? Because you would get these huge, more than a micron size boulders on the surface. It's really low surface area. So what he did was he developed solution chemistry based on amine oxidase or amine carboxylates in general. And those systems get very hot. So of course, increasing dispersion, the activity goes up tremendously. Some of these catalysts are 40C more active than the prior art. Is a really big deal because these catalysts put running in close to 300 degrees C starting temperature. Actually, they were changed out because of selectivity. The other aspect that came at the tail end of this was the discovery, this big one, of alkaline. Because now you can boost selectivity tremendously. And it was the first discovery was made chemically. Later on, they looked at higher alkaline metals. And it's important to realize the sequence of these discoveries matters. Because if you put alkaline metals onto silver without chlorine, it's worse. So in fact, chlorine discovery had to happen first, then the alkaline ones. There's a reason for it. You look back through the history. So if we look at this is just bare silver with chlorine, gas, upper 60s selectivity. You have the potassium, and you can see as you go upper potassium, you go. This is crucial. You have to alkaline optimize your DO tanks. If you don't do that, you're fooling yourself on what performance of that chemistry. They looked then, of course, at higher alkalis, Vidium, and then find cesium, and now you find mixtures of alkalis, patent literature, but you almost always find cesium as for alkali for optimized. And now you see the conditions that are typical. These are a standard set of conditions that were established from commercial operation shell units quite some time ago. We still use them as a screening tool because we've got such a long history of these tests under these conditions. We'll find these in our patent literature as well still. But now this is a typical average work rate on SPY for a commercial reactor. The early stuff was moderate. Vinyl chloride, most ethyl chloride or dichloride. And in those days, with this kind of invention, you were running in high 70s, maybe 80%. It was in the 70s. And now the pressures are up, the temperatures are down even more. Okay. So how do these things respond to chlorine? We've seen a lot of really nice talks about how chlorine's managed the surface, how important it is still in the operation of the Well, they realized, this is the same as for underloaders, that there's an optimum level that's necessary. And what you're seeing as you go through these inventions, as you add dopants to the surface, you can consider chlorine as a dopant as well, even though it's not equilibrium with the gas phase. As you go up in chlorine in the feed, for example, this just gives you an idea of the levels that are necessary, single-digit ppm levels of chlorine as ethyl chloride. The temperature requirement goes up for maintaining constant production rate. And this is the way we run our commercially is we don't run them at constant temperature rate, we run them at constant production rate because of the refining out straight product. You want to make as much as you can based on the unit's design. So the temperature goes up the life of the catalyst, but also as you increase the chloride concentration in these chemicals. At the same time, the selectivity actually is much lower. If you go to 0, as I mentioned, no chlorine with alkalis, it's worse than silver by itself, and with one. So what you see here is that the selectivity actually asymptotes. So where would you run this reaction? You could run it where the selectivity differences make much sense to increase the EC anymore, but at the lowest temperatures you get the most energy. So for this one, for example, you'd be running it at about 2.5 ppm. Remember this, because this is done for a long time, and this is a paradigm got established. This is how you run tests. Put it at constant chloride, and you run your test. Because the next example is the high selectivity came along in the 80s. And this was an invention by Anne Lawrence. Anne was the penultimate careful thought of the scientist. She saw that there's a promotion effect with cations. What about anions? She screened, I think, virtually every anion you could find in a textbook, and probably some that aren't. What she did was she discovered that green is brilliant. And again, this patent, if you look at it, talks about the combination of alkali ions and green. If you don't have the alkali ions, this doesn't work. So, in fact, this invention could not have been discovered without the alkali ions. Standing on the shoulders of giants. One invention has to be made. So, what she shows in this patent as well is that it's also important to optimize the alkali concentration to get the most out of the green. But if you look at the selectivity in this patent, it's higher. It's a big invention. But the real benefit of the green promotion wasn't realized because they were running at constant chloride. So what you find in a later patent is that as you change the EC from where you would have been down here to and you screen these chloride levels, you get a bigger advantage. And so now you're up well over 65%. If you go to lower conversions, of course, that gets even higher. But the really odd thing is that as you go up, chloride activity increases. This is the opposite of the previous generation catalysts. Very curious effect. So in this case, you would of course choose the EC level, chloride level, that would give you the most selectivity. Selectivity is always hard in commercial operation because otherwise, lower selectivity, you're burning valuable feedstock. You're burning it. And oh, by the way, you make more CO2. So as you go up to selectivity, you're actually greening out the process. Now, the other big deal here is that selectivities are now above what was considered a theoretical maximum. Now, fortunately, Anne, while she respected theory, never let it get away from the she would always tell me, John, just let the molecules do what they should do. Because there was a theory, I think most where in the field of 6 7s, it was actually developed by Shell researchers, Peter Kilty and Wolfgang Sockler, at the Amsterdam lab, that most people had thought, well, that's the limit. As soon as you get to 85.7, 6 7ths, why try eventually more? You can't tell Anne not to do so. That's why. So the other aspect of the catalyst that's very important, of course, is the activity. And just as a comparison, let me first go through how this compared commercially. So after this invention, it was rapidly scaled up, of course, and it was installed into Geismar plant in Louisiana, where they had a previous catalyst was our best high activity catalyst, which started out at about 79% in that plant at those conditions. And immediately we saw this huge benefit. This is all savings. This is all money. that much improvement. About a percent selectivity increase on normal work rate for operating plant, of course, depending on the cost of it, $1 million a year, easily, or more. But this, everybody wanted to go to isolation. So again, at low conversions, even in the commercial plant, this is running above theoretical maximum. So another mechanism that was proposed by this oxide, based on the super oxide, it wasn't the worst mechanism. In the meantime, I don't have time to go through these, but there are many advances made on the selectivity system over the years. As mentioned earlier, recently run into the 90% range or higher commercially at commercial work rates. So, and again, under the kind of conditions typical of a shorter lifetime, the high activity kettles. High activity kettles can run for several years, sometimes at wild conditions over several. These kettles do not. And one of the reasons they do not was that temperature stability, the activity stability, wasn't nearly as good as the high activity system. So this became a bit of an issue, right? Because if you're running this catalyst, you can only run it as long as your plant allows you to perform good temperature. I'll get into that in a little bit. But in about 2000 or so, Soled and some colleagues, Houston and Amsterdam, wanted to look into what is the, and a lot of work has been done in this area. What is the fundamental reason behind this trend in silver particles? The loss of activity in the system. We stop that. This high selectivity system could be a real winner. So we looked at it in a whole bunch of of course, did our bulk catalysts, our laboratory in Houston. In Amsterdam, I'll show quick examples. This is a whole other lecture, but I can't do it now. There's some 2D models ready for spin coating, electron beam lithography, and also with all else experimental work, we went in silico at Aeron. So just to give you some examples real quickly, we were looking at sintering. So this is wafer spin coating, and we have a reactor that was built in Amsterdam. You could test under real conditions, take these wafers, make them, and put them in there. You could pull them back out and do SEM imaging and see how these things develop over time. And as you might expect, you get things that look like planet Jupiter. But you go from really small particles to really large ones. And okay, that's great, but it's really hard to quantify these, hard to control the disposition of where the particles are and what sizes you start. So that makes it hard to quantify and control over. So we went to electron beam lithography, and some of these you can do under experiments on a chip. I'll show you one of the chips. Those days, the catalyst company was called CRI. So but we would have hundreds of patterns on one chip, and then you can put them into synthesis conditions, pull them back out, and we even, you just illustrate, you can write any pattern you want. Donald and Alda had them write the CRI catalyst logo on the chip. This became a gift for golfers or business manager. It just illustrates you really can, whatever you can think of as far as a pattern, put it on this chip, and then you put it into a reactor. So just a simple pattern illustrated in typical conditions, and this is a cesium note pattern in fact. The beauty of this technique, of course, is you can index every single spot. So the pattern is indexed. You can go back to the very same spot you were before, put it in our conditions, pull it out, get image analysis, and look at the same spots over as long as you want. And what you see, obviously, here is that you're sacrificing small particles at the expense of growing big ones. This is also all right. So, in effect, you're going to end up with all these big particles if you run this long enough. But what we're really interested in is, okay, what's the translational species that runs around between these particles to make them grow? That's when we went to work with Matt, his group. Some of the folks that are in the room are actually authors on some of the papers that came out of this work. But they looked at all different aspects of this process. So we have to take a silver atom or atoms from a particle, drop it onto the surface in some form, run it across the surface, reattach it to the bigger growing particle, and look at every single one of those individual steps. And that's what we did and finished. Find that analysis in these papers. It was really interesting. And this work does help guide research in where you should go, but it can also tell you where not to go. And that's just as important when you're pursuing commercialization of material at hundreds of metric tons at scale. So speaking of scale, just to give you an idea of kind of testing that we employ, we run things from milligram scale in high throughput units. We have a large reactor lab in Houston and one over in Germany, actually, it's a smaller effort, but gram scale testing units for screening. So we screen for formulations, we screen for stability and these kind of reactors. We also have a pilot reactor system. Kilograms into it. Now, this is important because you're looking at whole pellets relative to ground up materials, which you can push to. And then, of course, we go to full scale. What's remarkable is if you choose the conditions properly, you're testing right, you get performance that are grading across 10 orders of magnitude. But this is nice because, and the reason this works, of course, is that the eosynthesis reaction is not a diffusion limited case. So if you manage particles well, you can take data from milligrams, tens of milligrams, and get the same performance you would expect traditional using at full scale. So, and these full scale reactors for the uninitiated, they can hold 1 million pounds of catalyst particles, and they'll have tens of thousands of tubes into the shell design. So it's really remarkable to go from here to here. So now I want to introduce what we call the hybrid, because we have what happens between in the time when we have this high activity family, high selectivity family. Essentially, we ended up with a bifurcated market because we were selling these two catalysts, but not everybody could use the catalyst because of the reactor constraints and kind of stuck with this one. So they were high selectivity. They had tanks. They had decided to run these high selectivity. But so what we ended up doing was developing a catalyst that would run, and this is the issue. Most of the high activity plants were built with Caro or oil cooled systems, and they had a temperature limit that's about in this range, 627. So the high activity catalysts, of course, almost got to those limits. The high selectivity ones reached that in a short period of time, especially the early designs. Now, if you're selling catalysts, not that situation. If the customer wants to, we can just sell them a lot of different charges, but that's of course not practical. Turnarounds are designed around limits. And well, it's a real issue. Place catalysts every 8 months or so. So it wouldn't be done. So what we did was, I can't have time to go through them. I want to go through these examples. The hybrid catalyst is actually called hybrid because it would start out in activity like I had. And it would come up, eventually take on the same sort of activity loss rate that you get for a normal activity catalyst. But you had a benefit in selectivity between your previous activity and the high selectivity system. So whoever would run high activity catalysts normally, they would switch immediately to this catalyst. So it became a really popular catalyst. Placed a lot of the high catalysts in the solar market. There was another solution to the problem to low activity or a low temperature limiter in the reactor as well. And that was a process. Because remember back to the original report, it was saying that the CO2 is you call it anti-agent, anti-reactivity agent. And it's because, and we know this years now, when you have oxygenated silver and you expose it to CO2, you form carbonate. Carbonate blocks the surface. Essentially, you're smothering a breathing system. And so it can't activate oxygen. So, no. So in 2004, so we issued this patent illustrating that you can go to very low CO2 concentrations on the high selectivity system. You would take it from this sort of decline or selectivity to this one. So that what a lot of lifetime for people. And what they had to do is then upgrade their CO2 removal system recently. Became a very popular option for those users. But they may not want to do that. They might not want to spend the money on process change. So that led us to what we call now high performance one. We wanted to invent something that didn't lose the activity, but also had selectivity, like you have for these high selectivity calciums. Because a priori, we thought there's no reason why you can't get low from the fundamental aspect. In fact, if you increase the activity, you should be able to improve selectivity. So we had this sort of graphic. We wanted to get about 20 degrees C over current high sensitivity system. We wanted to get away from this region, which our business manager called the dog leg, because he was a golfer. This apparently looks like a fairway dog leg. And so we came up with this crazy, this is just to make sure we're all paying attention. We wanted to take it from the big dog to the little dog leg. So, and what we ended up doing was just that. We developed this system called the high performance catalyst. And just to give you an illustration, these are laboratory tests. This is laboratory data of the two. So here's a high selectivity catalyst, how quickly it would decline in those standard test conditions I showed earlier, as opposed to here's the high performance benching. So this very quickly became something that was commercial hit. And here's an example of the same commercial unit, same customer with the same conditions. So there's a previous high selectivity catalyst, and we have a second generation high selectivity catalyst that offered higher initial selectivity. And then they installed the second generation high performance catalyst, which by the time they were ready for it, we had the second generation out. So they were able to increase their average selectivity by about 3 points or so. And but really significant is their overall boost productivity by 24% without changing any part. So all they had to do is drop these catalysts. Yeah. Now, that being said, this catalyst was so stable, that it really wasn't being challenged by the conditions that this reactor was designed. These high selectivity catalysts, they ran for high turbulence material would run a long time. But what we realized was that we need to redesign the process around the catalyst, not the catalyst around the process. Because in a typical EO plant, you'll have 2 reactor trains that run in parallel, and then you have common downstream purification centers. And if you put the high performance catalyst in these, literally it's a challenge. So what we did was we designed a system where you have 1 reactor, shorter tubes, fewer tubes. And so now you can put this catalyst in, it's like a razor blade through a razor. And you can run this process with this catalyst as long as you do 2 reactors and 1 cabinet. So it's big savings for design, and it's become a very popular catalyst process design. It's gone out. So with that, I guess just about out of time, I wanted to end with saying that we've been in this for 90 years now. I hope we'll be around here with what happens when we hit a century, have the centennial celebration. But I hope got appreciated for was the history of how these things, all these different inventions came into play and how they got commercialized. Both the catalyst inventions, their contributions to what are common practice and process. And with that, I need to end with the additional acknowledgments. There's so many people involved in this kind of discovery, development, and commercialization. We can't name them all, but I need to go through some of them. Some of the retired folks, our current catalyst manager, my Paul McAllister, is here in the audience, and teams of people that are involved in various aspects of testing, invention, catalyst modeling, all of it. So, and with that, I'd like to close. Thanks for your attention.
Jen?
So, John, the 10 order of magnitude scale up is just amazing to me. And you mentioned there's no mass transfer limitation, which you need to be able to do that huge scale up. But what about the heat transfer?
Yes. So when I talk about the HP process, essentially you're like you said, you're limited by how much heat you pull out of the reactor.
Yeah.
So depending on different customers' designs, we have to calculate the heat flux, the heat load, and what they can remove in order to determine how high they can go in their work rate or ST1. So yeah, the process is designed to be much higher than 200, of course. But we sell it to customers units normally run at those rates, may run higher. But yeah, you have to know what you're doing, otherwise you have a runaway reaction. And you get away from the beauty of the fusion limitation. It becomes a problem.
Not trusted.
Yeah, I've always been fascinated by EO technology because I think that's a classic example of how catalysis can achieve decarbonization. Alluded to that. But there have also been processes that use hydrogen peroxide to get higher selectivity that have been reported in the literature. I know one of the downsides to that is the cost, obviously, of hydrogen peroxide as an oxidant, and also the carbon footprint of hydrogen peroxide itself. But then with the advent of hydrogen hubs and also oxygen hubs, and perhaps cheaper hydrogen peroxide, there is an opportunity to push that selectivity. It's like propylene oxide processes towards 100%. So what's your impression on that? Is Shell having thoughts on that possibility as well towards further decarbonization of this process?
Well, yeah, so certainly if you can get to cheaper H2O2, that would become a very viable process. As long as you can get a catalyst that's stable. Now we try to commercialize this hydrogen oxygen feed with propylene. And one of the issues you run into, of course, there's hydrogen selectivity to water. And that kills off and so it's said that you can be anxious. But yeah, if H2O2 could be made more cheaply, it could be a contender, so long as the catalyst will survive well under the conditions that you offer it. Yeah. Michelle is big into hydrogen, so yes, it's certainly something that we keep an eye on. Towards.
Thank you. Yeah, because time is up, so the share. Since joining Shell in 19